Right, so in the last episode we discussed saturation, which creates harmonics which are higher frequencies from a low harmonic, which is all very well and good. Let's say you've got a 1000 hertz, a 1k pure sine wave, and you create a harmonic at 2 and 4 and 8000 hertz or whatever. That's all nice and good. We can do that nice and easily within the digital realm. But what happens when you've got a 20,000 hertz signal and you want to create a second harmonic of that, and your sample rate is, say, 48k, which means, because of Nyquist theory, 24k is the maximum sample rate? Well, you can't do it. We did do a video about that. You'd think that's enough different levels, but realistically it's kind of half that. Effectively, just as a recap, the sample rate is the number of times per second that the measuring device, the analog to digital converter, stabs in and says, what's the voltage of the signal? And it will stab in so many times per second and say, this is the voltage of the signal. And Nyquist-Shannon theory says that the maximum frequency that you can sample has to be half of the rate that you sample at. So you need at least 2 points to be able to create a sine wave. And if you have at least 2 points, you can always recreate the same sine wave back, which is fantastic. But it produces problems when you're doing what we did in the last video, which is saturation. And to cure that, you have to do something called oversampling. And again, this can apply to all sorts of digital signal processing, not just audio, but I'm going to give it to you in an audio context because that's what I know. So let's start by drawing something very badly in the tradition of all geeky people that come on Computerphile and can't use a pen. So there is a sine wave. Let's say this is a block of time. Doesn't matter what the block of time is. So we've got 1, 2, 3, 4. We've done 4 full cycles of that. But if our sample rate only looked there and only looked there, when we were trying to reconstruct that wave, how would we get that wave back?
So basically what you're saying here is that sine wave is a noise, woo, or whatever.
Yeah, it's a pitch, it's a single.
Those bits where you've put crosses are where we're sampling.
That's where we're sampling the voltage.
You've only got those 2 points, so it's going to be one big wave between those.
So it's going to turn out sort of looking something like that, okay? Which means we've lost all of that data.
But also it's going to sound a lot different.
It's going to sound lower in pitch, so your, which I can't whistle, will end up being lower, okay? Which you really don't want that, do you? No. And this is the problem, is that, well, you could say, well, we're putting another sample point there, but then that's going to produce a sine wave that's like that, that's going to go through that. I'm not drawing this very well, so you'll have to forgive me on that. But regardless, if you try and put frequencies in that are way too high for the sample rate you're using, you're going to end up with lower frequencies than what you want. And the way it works, like the way it actually works, is that the more you go over, you basically measure the amount you go over and then you deduct that from your highest frequency, and that's the frequency it's going to produce. So for example, if your sample rate is 10,000 hertz, 10,000 times per second, so your maximum frequency that you can produce is 5,000 hertz. If you pass it a 6,000 hertz signal, it's 1,000 hertz above the limit. So that means it's going to produce a frequency at 4,000 hertz. So effectively we've got a ceiling, okay, of 5k, 5,000 hertz, and we've got 0 hertz, and we can put in any frequency between 0 and 5,000 hertz in our 10,000 hertz sample rate. And then the moment it gets to the top, instead of continuing and we get 6k above there, it will actually flip back down and mirror back down to 0 and then mirror back up. So by the time you put 10,000 hertz in, it will be back down to 0. And by the time you put 15,000 hertz in, it will be back up to 5,000 hertz. And it might, every now and again on the odd frequency, work musically. But trust me, if you're putting a 6,000 hertz signal in and you're getting 4,000 back, that's going to be inharmonic and it's going to sound awful.
So that could be just part of the sound you're recording, like, I don't know, one of the frequencies the guitar's making or something.
Exactly. So if you had a microphone that was over the top of a drum kit and you've got cymbal noise or something like that, or let's say you've got an analog measurement thing that's measuring the moisture in the soil, okay? And that is producing higher frequency voltage readings than your sampler that's then recording what they are and putting them in the spreadsheet for you to make your wave out of. if those things are mismatched, and if you've got higher frequency going in than the sample rate can take, you're going to end up with
incorrect samples,
and you're going to end up with a sort of anomalies in the frequencies that you actually care about. When you go above your frequency range and it reflects back down into something that you don't like the sound of, then that is called aliasing, and aliasing sounds horrible. So in the same way that we have with photos, although it's exactly the same, but there are aliasing filters, anti-aliasing techniques, and that's one thing I'm going to show you now. I'm going to load up Plugin Doctor to show you it in theory. This is where we had this nice little harmonic pattern in the last video. So all I did was just do input times input. So effectively I was squaring the input to get a pattern of harmonics, and then I was multiplying it by the sign just so that it wasn't making all the values positive, because squaring a number automatically makes it positive. So we were wave shaping in an interesting way. And our fundamental frequency here that I got was 50 hertz. If I just clamp that to 50 hertz, you can see. So if I've got a 50 hertz signal here, then our third harmonic of that is going to be 150 hertz because it's 3 times. Okay, and our fifth harmonic of that's going to be 250 hertz, and etc. So we can see this nice little pattern. But if I turn up this frequency, this pattern of harmonics here can't just keep going on above forever. You see what's happening the higher up we get. We're getting all these frequencies that are being mirrored down, which are completely inharmonic to what's going on. And you can see them traveling around. And you see, as I push the fundamental frequency up, you can see this second or third harmonic here, the nearest one to it, is then traveling down. It's traveling in the opposite direction.
So it looks messy. Would we normally see just one normal spike?
Well, really what you want to do is you want all of those harmonics to keep going up there and nothing to be happening below the fundamental frequency. But what's happening is as I showed in that diagram, as those harmonics are being created outside of the frequency spectrum, they're getting mirrored back down into the lower thing, which when you're dealing with music just creates things that just sound out of tune and sound horrible. It can do. I mean, sometimes it's a desirable effect on a keyboard or on a drum kit or something like that, but most of the time it's not something that you want, particularly if you're getting those harmonics into something that's actually audible. If they're sitting so quiet, then you don't care about it. But the other interesting thing is you can see as I move this frequency about, the higher it goes, then those get lower. Let's say I had a keyboard or a guitar where I was going, and I was putting some modulation, so the pitch was just slightly bending. Your frequencies and all your harmonics will all be moving together like that. But the mirrored ones that are coming down will be going in the opposite direction. So they'll be going down and then back up. Let me show it to you in another way as well, because you can actually present it on a sweep. Okay, in this software, which is lovely, I can actually have it as a 2D plot. I'm going to do it linear, and I'm going to take out some of the noise. But you can actually see here. So
that's loads of reflections. It looks like reflections. One of those when they put a laser into a mirror and it bounces.
Exactly. So what's happening there is you can see there's our fundamental that's going up nice and linear. This is our third harmonic, which is going up and it's hitting the top, and then it's coming back down, and then it's going back up. And if you were to listen to that, you'd hear at the beginning the sound go. If I generate a sweep here, and if I put not my dodgy plugin,
that extra little bit that just appears,
you know the little. I'll turn it down so we can talk. But what you'll hear is this chirping at the top end. So it's whoosh, whoosh.
Yeah, like a chattery type.
And if I turn up the distortion, I really go for like a heavy saturation. If I now turn on oversampling.
Oh, so it clips all that out because
it's gone. You're literally listening there to these frequencies bouncing off and interacting, and they're all added into each other and sounding awful, right? And how do we get rid of that? Well, let's go back to the paper for a minute, because I can't code that easily. It's not something I'm going to do, but I'm going to explain theoretically one way that, like everything, there's always 100 ways to do things, right? And all I'm going to show you is one way, probably what I would consider the most simple way. And the most simple way of doing it is, let's say you've got a very badly drawn wave, right? And we've got data here that's like sampling at a regular interval. So these are our data points. If we want to double that, you might think, well, actually what we'll do is we'll kind of in the background, we'll draw the wave and we'll just interpolate and add more data points in. But the easiest way to do that is to say, if this is our 0 line, I'm just going to put in some in-between points all at 0. So we end up with a wave that kind of goes to 0 and then up to there and then back down to 0, up to there, you know, to there, back down to 0, up to there. And it looks much crazier than the original wave. That is the worst drawing I've ever done. But basically what we're doing is we're zero padding. Do a nice animation, Sean, where you've got a wave and then each of the points in between are basically going to 0. What you end up with is let's change the other way, a bit like the frequency domain. If you had a signal which looked a bit like this, let's say on a spectrum analyzer, so we've got a load of low frequencies and then we got a little bit mid and then we got a load of high frequencies. So that's what it would look like on a spectrum analyzer. If you put zeros between each one, so you effectively double the number of samples, you actually then, if you analyze the frequency spectrum, because we've doubled the sample rate at that point, you actually get a mirror the other way of that. We would get another load of frequencies that would be that mirrored effect that we're seeing there, coming up the other way. Now, how do we then get rid of all of that? Well, that's simple. You know, we don't care about any of the frequencies here. So we just use an EQ to do low pass and get rid of all of that. And then we are left with our original signal, but at double the sample rate. So here again, I'm using Saturn II rather than my dodgy code to produce some harmonics. And you can see that there is clearly producing harmonics that mirror down and will give you that chirping sound. But you can see how very quickly, if I switch on their oversampling, so the good level oversampling, you can see how most of that goes and you're seeing very, very little. And if I put it up to superb quality, even more goes. So if I want to push that even further, you can see I'm still not getting any of that at all. But if I turn it down to just good quality, you'll probably get a little bit of reflection back. And then if I turn that off completely, you'll get all the mirroring and all the aliasing problems. So let's actually do this with some numbers. So let's say I'm going to have 0.8 as my first number. So that's going to be a point on the sine wave there. And then I'm going to do minus 0.8. So that might be down there. And then I'm going to 0.8 again. So we're basically creating some data points. So I've got an array of 4 numbers and I want to turn that into 8 numbers. So effectively I'm doubling the sample rate. I'm doubling the amount of data. If we put a 0 between each of those and 0 on the end, we've got 8 numbers, okay? We've got 8 numbers. Now that will then look and sound dodgy, okay? Because it will be doing the equivalent of what we're seeing here, where each inserting all of those zeros will make every frequency also create a harmonic and mirror in the upper frequencies. So if this is your frequency, okay, and this is your amplitude, and we've got some stuff sitting in the low end and we've got some stuff sitting in the middle end and we've got some stuff sitting in the high end, which is louder, and we double the sample rate, that high frequency is then going to end up in the lower part of this, and the mid will end up even higher and the low will end up even higher. So you'll end up with a mirror. So put my hand there. You double the amount of samples, put all the zeros in, and you end up with a mirror of the frequencies, but just mirrored the other way in the same way you see that. But obviously with the magic of EQ, we can just come in and chop all of that out. And then all of these zeros, if we run it through, like in the first video, remember I had that low pass filter and it was just a moving average? Mm-hmm. Well, if you ran the moving average over that and you were looking at averaging those two and then averaging those two and averaging those, and you do that, you can see those zeros will stop being zeros very, very quickly. And you end up back with a smooth curve, but with double the amount of points. And that's just a really important thing to do in audio and probably many other disciplines. That's pretty cool, isn't it? Being able to play with audio like that, literally in a plugin, just start writing C. So I wanted to introduce you to that because